Hey everybody, it's Mr. Canfield. Today we're going to be in chapter 29, Riemann Sums, and there's some problems. We've got 26, we skipped 27 and 28, and we're in 29. We're actually going to call 29 27, and we're going to call 27 29. I think some errors in copying have happened, but anyway, welcome to the wonderful world of Riemann Sums. So we got to talk about Riemann. His name was Bernard Riemann. I don't know if they rolled the R's in Germany, but it sounds more fun that way. Bernard Riemann. Anyway, Bernard Riemann. So you want to do like Rick and Morty, Ree, and then Mann, not man. So like Mann. Oh, like come on. So Riemann, his Bernard Riemann. It's again the reason why we want to know how to pronounce people's names correctly is so that when we're talking about them, we sound smarter than we actually are. Because in college, someone's going to go, "I don't know what a Riemann sum is," and you're going to go, "Oh, you don't know what you're talking about." And then somebody else is going to say Riemann sum, and you're going to be like, "Okay, they've probably heard of these before." So anyway, it is like. It's not a big deal at all. He doesn't care. Because he lived in the 1800s. So anyway, we're going to talk about the area problem. And the area problem was one of the biggest problems that Newton was trying to solve when he was coming up with calculus. So, for example, if we have some curve like this, what Newton did, or what we can do to kind of think through these, we're basically going to do math history lesson right now. I could make a series of rectangles where I could find the y value of this curve. Let's say this is x squared plus 1. I could find the y value of this curve here. And let's go from 0 to 4, okay? And I'm gonna make 4 rectangles to try to approximate the area underneath this curve. So, like if I make a curve right here, if I make a rectangle right here, well, let's talk about the area of this rectangle. So the area of this rectangle, I could say is, well, the base would be 1, and the height would be whatever the y value was right here. So if I want to find the y value right here, I could plug in my x value of this into my original function. I could plug in 0. So 0 plus 1 is 1. So area is 1 times 1, so 1. Okay. Then what I would do is I would make my next rectangle. And I could say, okay, well now I'm going to go up to this y value, go straight over, and come down. So what's this y value? Well, where do we start? We start at the x value 1. So let's talk about this rectangle. So its area is going to be, well, what's its base? Its base is 1 again. What's its height? Its height is going to be, well, whatever that y value is. To find the y value, I'll plug 1 in here. So 1 squared plus 1 is 2. So I get an area of 2. So we got an area of 1 for our first one, an area of 2 for our second one. To find our third one, it's more of the same, just a different y value. I'll start here and go find the y value. Let's see, the y value here, let's see, this is just, x equals 2. I'll just plug in 2 here. I'll get 2 comma, let's see, 2 squared is 4 plus 1 is 5. So, and then I'll go straight over and drop it down. So with that, let's see, the area of this rectangle is, well, the base is still 1. The height this time was 5. So the area is 5. unintentionally have like Kenya colors here. When I was in second grade, we studied Kenya, and I love its flag because of that. So thank you, Mrs. Davis. Lastly, it's red again, but it's a different writing utensil. So lastly, we'll start here, we'll go up, find the y value, go over, go down, and that'll be our last rectangle. So in this one, our base was 1, and our height was, well, let's see, the x value was 3. So when I plug in 3 here, I get 3 squared is 9, plus 1, I get 10. So 110 area is 10. So these 4 rectangles, if I were to add them together, 1 plus 2 plus 5 plus 10, we get 3, 8, I get 18. This is the approximate area under y equals x squared plus 1 from 0 to 4. So it should be pretty apparent. These 4 rectangles added together, this is not the exact area underneath this curve. We've got a little bit of space there, even more space, and then, whoa, look at all that space underneath. So we're definitely missing stuff. This estimation is too small. So we could do a different kind of estimate. So I don't know if you noticed, each time we started out, we made our rectangle, we went up the left-hand side and went over and down to make our rectangle. What if we did the exact same thing, exact same function, everything the same, except instead of going up the right-hand side of this, what if we started out, the left-hand side of it. What if we traveled up the right-hand side, found that y value, went over to the left and down? So let's try this one out. For our first rectangle, we'll say the area is, well, it's, this was y is equal to x squared plus 1. I'm going to save myself a little bit of time. X, y, 0, 1, 2, 3, 4. So I plug in 0, I get 1, plug in 1, I get 2, 2, I get 5, 3, I get 10, and 4, I get 4 squared is 16 plus 1 is 17. Okay, so I went up, I was at 1. The base was still 1, but what was the height? At 1, it was 2. So the area of that rectangle is 2. Well, for our second area, see, I used red pencil last time. For our second area, we'll take this rectangle here, we'll go up to here, we'll go up to that y value, go over, and go down. And so you might even notice already, the area that we get for this one, the approximate area, is going to be too much. So you can say this area is, the base is 1, the height is, let's see, 1, 2, the height at 2 is going to be 5. So this one was 2, this one was 5. Our third one, same deal. We'll go up the right-hand side, go over, go down. That one's going to give us, area is still just a base of 1. The height this time, when x is 3, was 10. So that's going to be 10. And then our last one, all right, our last one is going to be, still has a base of 1. This time the height, it goes up when x is 4, and it's 17. So this time, if we add these together, 2 plus 5 is 7, plus 10 is 17, plus 17, we get an area of 34. So previously, our estimated area was 18. Now our estimated area is 34. the real area is going to be somewhere between those two. And there's a couple of ways that we could get a better area. So let's just, for a moment, pause and oh, would you look at that? We're using the same function. It's almost like I knew this was happening. All right, so I'm doing it slightly differently than he did. He's using 2 rectangles, then 4 rectangles, then 8 rectangles. So what I think is worth mentioning here is this is an overestimation in this case. This is an underestimation in this case. And we're going to come back to this more and more. But if you notice, with concave up functions, any concave up function is going to have this situation where the right-hand ones, we call these right-hand sums because we're going up the right side to get the y value. We call these left-hand sums because we're going up the left side. With right-hand sums, they wind up being overestimations when we're dealing with concave up, and with left-hand sums on concave up, they wind up being an underestimation. Wouldn't it be great if we could just like find somewhere in the middle? So we're gonna see that in just a minute, but I think it's worth looking at his diagrams really quick. You can see we have, this is the perfect area, exact. Then here's just with 2 rectangles, and you can see with 2 rectangles we have all this space over it that is too much. It's an overestimation. So what if we double the number of rectangles and go to 4 rectangles? So now you can see there's still a lot of space over it, but it's also significantly less. We're missing chunks of this. We're missing chunks of problem space. And then if we were to double the number of rectangles, again, we'd have even less problem space. And so what the fathers of calculus did was they were like, wait, let's go to an infinite number of rectangles. So we'll get there eventually, but whenever we're doing Riemann sums, we're really just kind of tiptoeing through those old ideas of, oh, how many more rectangles can I have? So, how many more rectangles can I have? That doesn't make any sense. What I'm meaning to say is like, oh, okay, we would have done this and then gotten more and more rectangles, more and more rectangles. We're just appreciating what's already been done. So, I'm going to do 2 more sums, because this is generally how I deal with Riemann sums. So we're going to take our x squared plus 1 again. And this time, instead of going with 1, 2, 3, and 4, and going up from the left side or the right side, I'm actually going to go dead set in the middle between 1 and 2, and I'm actually going to find the y value at 1/2. And when I do that and go left to right, you might notice that looks pretty good. Similarly, between 1 and 2, I'm going to try 1.5. And so now it starts to show a little bit. A little bit of this winds up being outside, a little bit winds up being inside. This allows for a little bit of overestimation and underestimation at the same time, meaning that we've got an even closer estimation. So, to find these, wait, you know what? Hold on a second. For all these situations we've had so far, instead of writing together 4 different areas and then adding them, I could have just said, what's the area of this? Well, it's the length times width plus length times width plus length times, or base times height plus base times height plus base times height plus base times height. This is silly though. They all have a base of 1. I've given them a uniform base, so I could just pull that base out front. And it's like height 1 plus height 2 plus height 3 plus height 4. And my base here was 1, and then I just say, well, find my different heights and add them up, and then multiply by 1. It's going to save us a ton of time. Same thing here, right? These were all being multiplied by 1. If the base was something different, it would be more significant in these situations. But I picked a base of 1 just to keep the calculations easy, and Stu did too. At least for 4 rectangles. So anyway, So if we're going to do this one's called the M sum. The left hand sum is called the L sum. The right hand, this is called the R sum. Guess why? Guess why M is called the M sum? It's the midpoint. It's the midpoint sum. Okay. So I need 4 new y values though. I'll need the y value at 0.5. And then I'll need it at 1.5. Then I'll need it at 2.5. Then I'll need it at 3.5. So, cool, my calculator's dead. You could totally do this by hand. Don't. Like, okay, cool, yeah, I can do this by hand. I don't see a lot of, I don't want to do it. Cool, I got that. I'm gonna go on my table and I'm gonna do independent ask under table setup. Go to my table. I wanted 0.5, I wanted 1.5, I wanted 2.5, and I wanted 3.5. Gee, here they are. 1.25, 3.25, 7.25, 13.25. So if I do all that, and I add those together, let's see, those all add up to 1. So I'll just tack another 1 on the top. 1, 2, 5, 12, 25. So I got that when I added them together, and I'll multiply. So my area is equal to base. Each of these had a base of 1 times my height of 25. So area is 25. Area is 25. Wow. Area is 25. Okay. So you might be curious about what the actual area is because we keep getting closer and closer and closer. So I'm gonna just go and figure it out really quick. Let's see. Actual area, actual area. The actual area is 25 1/3. So this is really, really close. And that's only at 4 rectangles. Imagine what would happen at 57 rectangles or at 8,000 rectangles. The thinner those rectangles are, the less space there is that we're missing. But no way am I doing that. I could write a computer program to do it though. Okay, we have one more sum type that we have to talk about, and it's called the trapezoidal sum. No, trapezoidal sum. So let's just review for a moment how a trapezoid works. Welcome to a trapezoid. These two sides are parallel. It's not a parallelogram though, because the other two sides are not parallel. They can really be at kind of any angle we want. In fact, we could go like, oh hey, here's a trapezoid that looks like this. You know, throw a right angle on there if we wanted to. I don't know why we'd want to, but we could. So anyway, the way that we find the area of a trapezoid is the area of a trapezoid, we really cut this other triangle off. No, that's not how we do it. I don't remember how. Let's see, what is it? Do we bring this over? Do we like tack this down? No. There's like some extra area on there. You average the bases. We've got 2 different bases, you know, because like the area of like a parallelogram like this, the area is equal to the base times height. Even if your height, you know, winds up being, you know, with some part of it sticking out of the thing, it works just the same as a rectangle. Just you have to find the height instead of finding, you know, the length of a side. So trapezoids are very, very close to this. The problem is the bases don't have to be the same length. They can be like this. And so the area of some trapezoid is going to be, the area is equal to the basis average times the height. So the way we find the basis average is if we call this one base 1, we call this one base 2, we'd say the area is equal to base 1 plus base 2 divided by 2 times height. Right, you add them together, divide by 2. So generally we'll write it 1/2 b1 plus b2 times the height. And that's the area of any trapezoid. So you might be thinking, well, how am I supposed to do a trapezoid under a curve? This is where this guy that I crossed out comes into play. Turn it sideways. This winds up being a really nice way to do area under a curve. So same curve, x squared plus 1. I'm going to pull out my, let's see, 0, 1, 2, 3, 4. Height was 1, and then 2, and then, what was that, 5, 10, and then 17? Yeah, okay. So just recalling them from earlier. So what we do is we draw a trapezoid where the base is no longer the base. This is the height now. And we have these two separate bases, and then we connect them like that. And we get a really nice snug fitting shape. So like here, you go like this, then connect the dots. And I'm dealing with thick markers here, so you can't see any of the space, but there definitely is space. It's still not perfect, but we get a really, really nice. And so the way that it works is the area of one of these, well, this time the area, they're all going to have the same height in common. And then my different bases are going to be this y value and this y value. So height, and then we'll divide it by 2, right? So 1/2 height, and we'll get 1/2 height times base 1 was 1, base 2 was 2, 1 plus 2. And then the area of my next one is going to be 1/2 times my height. Oh, my height's just this, which is 1 times 1. So this is 1. So then 2 and 5. 2 plus 5. And then area of my third one, well, the height's still going to be 1, and the height's going to be 5 and 10. And then the last one, 1/2 times, height's still 1, 10 and 17. So we wind up having all these little, togethers. Check this out, though. If I add all 4 of these together, this plus this plus this plus this, they all have that 1/2 and that 1 in common. So I could say the area is actually equal to 1/2 times 1 times 1 plus 2 plus 2 plus 5 plus 5 plus 10 plus 10 plus 17. Do that. Wait a minute. This happens twice, this happens twice, and that happens twice. The two ends don't happen twice. Everything else happens twice. So oftentimes, the way that people do these quickly is to go 1 plus 2 times 2 plus 2 times 5 plus 2 times 10 plus 17. In reality, this might not be any faster for you than finding them individually and adding them together. But at the end of the day, if we go in here, 1/2, let's see, that's 4, 10, 20, and then there's going to be 18 with the 1 and 17, 18. So 18, 38, 48, 52. We get an area of 26. So in this situation, the area of 26 winds up being slightly less precise, or slightly further away from the real area than our midpoint sum. And the times that I've done these, I find midpoint sum usually is closer, but these are both very close to the real thing. And this is only with 4 rectangles, or 4 trapezoids. Imagine what we would do with 80 bajillion because that's totally a number. So this is Riemann Sums. So he goes through it a little bit differently than me, but I wanted to, I said Riemann, didn't I? So it's a Riemann Sums. I make such a big deal out of it, and then I said it, the more Americanized way. So when Stu goes through this, he's showing us his work, he's showing us what he's thinking of, and it's, just a bunch of different things for us to go through and try different sums. So, yep. But yeah, that's Riemann Sums, and that's how we're going to approach them in my class, at least. So, hope this was helpful, thinking through the different ideas, and if you need more, definitely look through his notes. There's a lot of good stuff. Bye!